All right. Now the class recording has started. So, are you okay? Are you just gonna have to like hold it? All right. So, like we said, the next couple days, I want to start looking at the relationships between acceleration, velocity, and displacement. Changes in one causes changes in the other one. So yesterday, we were looking at a non-accelerated motion, or we started looking at a non-accelerated motion, or a constant velocity. If something has a constant velocity, right, its acceleration is 0 meters per second. Never changes. So when we look at an object, if we look at this picture, each of these pictures of the ball represents 1 second worth of time. So each second that goes by, the object continues to move that same distance because the velocity never changes, right? So the speed remains constant. When it gets to the wall, it's still going 1 meter per second. It will take 5 seconds to move 5 meters because in this particular case, the velocity was 1 meter per second. Regardless of what the velocity is, if the acceleration is 0, that velocity will stay constant the entire time. Okay, good there? But then we started looking at this situation that shows this guy riding his bike at 1 second intervals, and we see that they are not evenly spaced, right? Looking at the information that they gave us, we can see that his instantaneous velocity, okay, are we good with that term? Yes. The velocity at one particular moment in time, 1 second after he starts pedaling his bike, his instantaneous velocity is 2 meters per second. 1 second after that, his velocity has jumped from 2 to 4. 1 second after that, his velocity jumped from 4 to 6. So we can see here that his acceleration is 2 meters per second because his velocity keeps changing by 2 meters per second for every second that goes by. Is that good? Okay. Because this is a nice even increase in velocity, if we went to graph these velocities versus time, I think we talked about this yesterday, right? This is going to look like what on a velocity versus time graph? On a velocity graph, what is it going to look like? It's going to look like a straight line. Not a horizontal line, but a straight line. Here, I can draw it, so why don't I do that, right? Right? If this is velocity and this is time, right? At 0 seconds, the velocity is 0. At 1 second, that velocity has jumped to 2. At 2 seconds, the velocity jumped to 4. At 3 seconds, the velocity jumped to 6. If we connect the dots, which I know we're not supposed to do, but, right? Okay? We end up with a straight line. What do straight lines on velocity versus time graphs represent? Not a constant acceleration, right? What would be the slope of that line if it represents the biker?
A linear one.
Well, yes. Specifically, the slope would be 2, because the acceleration is 2. Right? Is that good? Okay. And then right at the end of class yesterday, we talked about the idea that mathematically we can represent this pattern with this equation. Right? We're discussing scientific laws in this section. What do laws do for us? What does a scientific law do for us? It tells you what, but it doesn't tell you why, right? This is all just telling what. It'll tell us what the final velocity is if we know the initial velocity and the acceleration, how long we're talking about. Okay? Good there? All right. The next picture that you have adds a little bit more detail to this guy's bike riding experience. Not only do we have the instantaneous velocities up here, now we've added some displacements down on the bottom. Okay? Way back at the beginning of this unit, we talked about this equation. Okay? Does that look familiar? Yes, hopefully? Right? That's our definition of what? Average velocity. Okay? This problem's a little bit different though. Because what is continuously happening to the velocity? It's continuously changing, right? We know how much it's changing by, but it's not a constant velocity. So to figure out how far we go, we just can't take the velocity and multiply it by the time. Because the velocity isn't constant, right? Okay with that so far? So, let's talk about one specific interval, this interval right here. Okay? From the picture, we know that that velocity increases from 0 to 2. Yes? But he only went 1 meter during that time. Okay? If his velocity was a constant 2 meters per second, how far would he have gone during that second? 2 meters. But he only goes 1 meter here, right? He doesn't reach 2 meters per second until he gets to this line. The rest of the time, he's gradually speeding up to that point. So he's not going to go 2 meters because he's not really traveling that fast until the very, very end. Does that make sense? Okay. However, we can look at this interval and look at his average velocity. Okay? If he starts at 0 and ends at 2, what would be his average velocity during that time? Well, in this case, it tells us how much time are we talking about here. 1 second, right? Okay. So his average during that time is 1 meter per second. Okay? You guys know that because you learned in math class how to take averages, right? How do you take the average of something? Add them up. Divide by the number of things that you added up. We can do the same thing here with these velocities. If we know the initial velocity during some interval, and we know the final velocity during that interval, we can figure out the average just by adding the two of them together and dividing by 2. Good? You okay with that? So, how does that get us to 1 meter? Well, here's 2 equations that I just wrote up on the board. What do you see about those 2 equations? Notice anything about them? They both equal average velocity, right? So you learned sometime along the way, whatever this property is, right? If A equals B and B equals C,
Then A equals C.
then A equals C, right? What is
What?
the transitive? Is that what it is? The transitive property? Okay. All right. Well, you learned it a week ago. Now we're going to apply it, right? If A equals B and B equals C, A equals C. Yes?
Yeah.
Okay. And then doing a little algebra. I can rearrange that equation to make it look like that. Does everybody follow my algebra there? And how did we get it? It's up there. See that plaque that's right next to the flag? Kinematic equations.
That's the last one.
Tia, Ken's, Kelson. They're former students. So, well, they were former physics students, and when in physics, I think we discussed this. You get to go to Cedar Point, and so yes, not in this class, in physics. So
All this physics?
We know.
all of them.
So we have to go to Cedar Point for
I don't know.
Yeah.
So, but anyway, so here we can figure out a way to determine how far something goes based on how much the velocity changes. Right? Let's take a look at this interval from here to here. Okay? That green interval. What's the initial velocity of this green highlighted interval? The initial velocity of this interval that I highlighted in green. What's the initial velocity? 2 meters per second. What's the final velocity? 4 meters per second. How much time goes by? 1 second. Okay? So if we take that information and plug it into this equation, right? What's 2 plus 4? 6. Multiply that by 1/2. 3 times 1 is how far? 3 meters. How far does the picture show that he went in that time? 3 meters. So it's good that we get the right answer when we do these things. Okay. So now we have 2 equations. Sorry, I guess we'll write some things down. So 2 equations that I've introduced to you so far, right? This one tells us how much the velocity changes when we're accelerating. It tells us the instantaneous velocity at any point. This one's also up there, right? This one tells us how far we go if we're accelerating for a certain amount of time. Okay? Good? Flip it over to the back of that page. So there's a picture of a ramp. Oh, here. I'm going to use lots of colors up on the board today, so if you would like some colors, I'll put these out so you can keep track of things as we go. All right? Please share if you know. Whoa. That totally makes you better than her.
Yeah.
So,
Yeah.
so,
All that.
If you need it for today, like I've got something for you today. I would say if you needed it for today. All right. At the top of your page is a little description about this ramp. So first, at the top of your page, it's labeled as accelerated motion, right? Meaning what's going to happen here? It's going to accelerate. That means or it's going to change. Its velocity is going to change, right? Generally speaking, that's what accelerated motion means, right? In this case, in particular, what's going to happen to that velocity? It's going to speed up. All right. It says uniform acceleration occurs for a ball rolling down an inclined plane. Uniform acceleration is the same thing as constant acceleration, right? It is constantly accelerating. It says this ramp or this plane below is tilted so that the ball picks up speed of 4 meters per second every second. That is, its acceleration is 4 meters per second squared. Right? That's what I have it listed up here. We said that we can also write this like this. Yes? Those are the same thing. Okay? All right, so let's talk about the two things that we want to find out on this ramp. Okay? First, just like before, each picture of the ball rolling down the ramp will represent 1 second worth of time. That makes doing our math calculations a lot easier. Okay? The ball at the very, very top of the ramp, it says v is equal to 0. At that point, t is also equal to 0. Right? So that's the very beginning when we first start measuring this ball rolling down the ramp. Okay? The next picture represents 1 second later. How fast will that ball be going 1 second after it starts rolling? 4 meters per second. Good? The next picture is 1 second later. How fast will it be going at that point? 8. The acceleration tells us what? The increase in velocity, right? I guess more generally it's the change in velocity, but in this case it's increasing, right? How much does that velocity change every second? Right? Next, 1 second later, how fast is it going to be going? It's going to be going 12 meters per second. 1 second after that, how fast is it going to be going? 16 meters per second. And then finally, at the very, very bottom of the ramp, how fast is it going to end up going? 20 meters per second. Okay? Good there? We said that the mathematical relationship that represents that looks like this. VF, we said, represents the final velocity, or we could also say it represents the instantaneous velocity at any point on the ramp. VI is the initial velocity. In all of this ramp, what was the initial velocity? 0, right? A is the acceleration, and then T represents what? How much time we're talking about. So we just figured out, because we understand acceleration and what it means, that the velocity at that point was 16 meters per second. If we use our equation, we should get the same answer. We already said, what's the initial velocity of this object on the ramp? 0. The acceleration of the object on this ramp is what? 4. That spot on the ramp is how many seconds after it started? 4. Right? So if you solve that equation, 0 plus 4 times 4. 4 times 4 is what? 16. So the final velocity after 4 seconds is 16 meters per second, just like it's supposed to be. Okay? Next question. How far does it go during that time? Nope. It would go 16 if the velocity was constant. What? Well, let's do this. All right? This equation relates to us how fast we're going at the beginning, how fast we're going at the end, how long did we go. So for this part that I've highlighted in pink, what's the initial velocity? 0, right? So we're going to put the 1/2. 0 goes here. What's the final velocity during that section I highlighted in pink? 16. How much time are we talking about here? 4 seconds. 0 plus 16 is what? 16. Divide that by 2. 8. Multiply that by 4. How far did it go? 32 meters.
You were 8 off.
Just close.
It said 30 or
Does that make sense how it all fits together there? All right. Yes, no? All right, let's do this. Let's talk about the whole ramp, right? We've already established the fact that the final velocity down there is 20, right? If we want to talk about how long this ramp is, we want to know displacement. How far does the ball roll when it goes down the ramp? That's the equation that relates for us displacement along with the initial velocity and the final velocity. All right? So for the whole ramp, what's the initial velocity? 0. What's the final velocity of the entire ramp? 20. How long does it take to get down the ramp? 5 seconds. 0 plus 20 is 20. Divide by 2 is 10. Multiplied by 5 is 50 meters. Okay. Do we see how those things start fitting together? Okay. Tomorrow, we will look at first, here's a suggestion I might have for you. See the next page in your packet? I know there's no formal homework. The next page in your packet is a ramp that is tilted so that the acceleration is 5 meters per second squared. See if you can fill in that chart. How fast was the ball going? How far does the ball go? I'll show you answers tomorrow at the beginning of class. Okay? Then we'll get into some gravity. Objects moving under the influence of gravity.